Excellent. So up here, I have the graded stuff from last week, chapter 3 quizzes, your last lab. All those grades have been up on Blackboard. I'll just heard a ding, which one do you think? Oh, that's not important. Okay. So things that are due. The chapter 4 homework is due on the 19th. That's not this week, but next week, Wednesday. That will also be when the chapter 4 quiz will be. And then the test on chapters 3 and 4 will be the Monday after that. So not next week, but the week after. And I'll, go over that again as we get closer. But we have a bit until that test. There is a lab today. It'll be on momentum. There will be a lab next week as well. So, continuing on with chapter 4, we were talking about work and kinetic energy. So, work is force times distance. Kinetic energy is 1/2 mass times velocity squared. And if you do work on an object and include the work from all the forces acting on the object, the work is equal to the change in kinetic energy. Kinetic energy final minus kinetic energy initial, or 1/2 mv final squared minus 1/2 mv initial squared. And one of the nice things about work and kinetic energy is these don't have directions. You don't have to worry about vectors and adding vectors or anything like that. They're scalar quantities. The distance is in the direction of the force, or the component of the force in the direction of the distance. Force in the direction of movement times distance. That is what work is. You can also work it out as distance in the direction of force times force. They work out to be the same thing. Now, for energy, we can also talk about a concept of potential energy. And that is energy from various forces that have a quality. They're called conservative. What that generally means is that if a force is conservative forces are forces where when you do work against them, you can get that work back. So if I lift this weight up, I am doing work against gravity to lift this weight up. I can get that energy, that work back by letting this fall. I'm not going to drop this weight because it'll damage the table. But the primary form of potential energy we're going to deal with is potential energy due to gravity. Since work is force times distance and weight, mg is a force. If we substitute in height for distance, we get that potential energy is mgh. So that's energy stored in position. So this weight down here has less energy than up here because I could drop it and get that energy out. But that's, stored because of its position relative to the Earth. It's stored in gravity. You can also have potential energy stored in springs. So if you bend a spring, there's energy stored in the spring, and then that can be released. And there's a bunch of other ways you can have potential energy, but those are the ones you're going to run into on a day-to-day basis. We're really only going to deal with gravitational potential energy in this class. Because the spring one's more complicated. We're just going to deal with only gravitation. So the gravitational potential energy is equal to the work done, and this is equal to the weight times the height. For gravitational potential energy, you can measure height from anywhere. So potential energy can be negative, but you need to keep measuring your height from the same place for the entire problem. That's the important step. So for example, potential energy, how much work is done lifting a 1 kilogram book to the height of 1 meter. So here is a 1 kilogram weight. If I lift it 1 meter, how much work did I do? Well, work is mass times the acceleration due to gravity times height. So 1 kilogram times 9.8 meters per second squared times 1 meter. This action, where I lift this 1 kilogram weight up 1 meter, I do 9.8 joules of work. And it is gained 9.8 joules of potential energy, which I could get back, if I have this on a string and around the drum, I could use it to like power a clock. So if you've seen the grandfather clocks traditionally use a big weight slowly lowering to power the clock. And it's just a way to store energy. Now, the nice thing about potential energy is that potential energy doesn't care about the path you take. It only depends on the initial and final positions. It is independent of path. It turns out for a force to have a potential energy, it has to be independent of path. Those two facts are actually tied together. So if you disregard any frictional loss, it takes the same amount of work to lift a mass straight up as it does to slide it up a slope to the same height. The difference is when you're sliding it up a slope, you use less force over a longer distance, and you get the same amount of work. Is basically what happens. It's the slope means you don't have to use as much force to push it up the slope. That's what an inclined plane does for you. You use less force, but the exchange is more distance, and you end up doing the same amount of work. So you can also think about the work you do to an object where you ignore these conservative forces as change in potential energy. The work is done when there's a change in position, like I did work to raise this up. If you want to be strictly accurate, I did positive work, gravity did negative work, the work can be got back. But for potential energy, it just becomes convenient to ignore the work done by gravity and treat it as potential energy. And so the reference point for measuring heights is arbitrary. You're actually only interested in the change in height for a problem. So it doesn't matter if you went up from 1 meter to 2 meters or if you went from 0 meters to 1 meter. It's still the same change in height. You'll have the same change in potential energy. So here, for example, you could be going from negative 50 to 50 or from 0 to 100, but it's the same change in height. Distance is 100. So no matter which scale you use, the change in height will be the same. So it doesn't matter where you choose your 0 to be. So you can choose your 0 for wherever is convenient for the problem. The important thing is that you stay consistent with your 0. It has to be the same throughout the whole problem. But often it's good to choose one of your starting positions as your 0, just because then, you have 0 for one value. Either your starting position or your ending position is 0, because then you have 0 for one value, or you might have a given, you might have given heights in the problem, and you can just use the heights that are given in the problem. Just whatever's most convenient. So other things, the other more common source of stored potential energy you're going to run into, that's not like complicated chemical energy, like electrical stored energy, but springs. Springs store energy in deformation, in bending. And bowstring, actually, for a bow, the string doesn't actually store much of the energy. Most of the energy is actually stored in the bending of the limbs of the bow. The string is not very elastic. But springs, they're all basically springy things. So here, if you have a 2 kilogram block and you raise it 2.5 meters, by how much does its potential energy increase? So remember, G is 9.80 meters per second squared, and potential energy is mgh. Mass times G times height. Therefore, potential energy is mass times G times height, mgh. So 2 kilograms times 9.8 meters per second squared times 2.5 meters, which comes out to 49 joules. Units are going to be joules because it's energy. Again, the nice thing here, you're just interested in the change in height. You're not worried about like paths or directions. There's no direction here. It's just a number. Now, if I change the potential energy of a 4 kilogram block by negative 49 joules, I decrease its potential energy by 49 joules. How far do I lower it down? Remember, potential energy is mass times G times height. And this is a 4 kilogram. The mass of the block is 4 kilograms. And its change in potential energy is negative 49 joules. So change in potential energy is going to be mg times change in height. We want to find the change in height. So the change in height is just going to be the change in potential energy divided by m times g, the weight. So minus 49 joules divided by 4 kilograms times 9.8 meters per second squared gives you negative 1.25 meters. This is lowered by 1.25 meters. The distance the block was lowered is 1.25 meters. If it requires 147 joules of work to raise a block by a distance of 10 meters, what is the mass of the block? Potential energy is mgh. Mass is potential energy over gh. The mass is 147 joules over 9.8 meters per second squared times 10 meters. Mass is 1.5 kilograms. Oops. Mass comes out to 1.5 kilograms. And then lastly, if I move a 2.5 kilogram mass from y equals negative 6.5 meters to positive 9.5 meters, what's the change in potential energy of the mass? So this is where we aren't starting at 0. We're starting at a known value and going to another known value. There's sort of two approaches you can take. You can find the potential energy for each position and take the difference. Or you can use the fact that change in potential energy equals mg change in height. Kinetic energy? Yes. There is no kinetic energy in the cloud. Oh, okay, yes. No, generally, yes, good. Look at the right. Velocity needs to be in meters per second for kinetic energy because that will give you joules. If you use different units, you get different units out. Okay, so here, potential energy is mgh. So change in potential energy is going to be mgh final minus mgh initial. We could calculate each of these individually, or do a little algebra, and we can see that it's mg times change in height, h final minus h initial. So if we plug in our numbers, 2.5 kilograms times 9.8 meters per second squared times 9.5 minus negative 6.5 meters, which gives you 24.5 newtons times 16 meters, or 392 joules. And we're subtracting a negative, so we add. But yes, for kinetic energy, you would use meters per second. Everybody got this? So one of the interesting things that happens is that if there isn't any friction or such, it turns out energy can neither be created nor destroyed. Now, in everyday life, energy seems to get lost. But usually it's lost to things like friction. In that case, it's actually being turned into heat. It's always changing from one form to another, and it is always conserved. So the total energy of an isolated system will remain constant. So the total energy at time 1 will equal the total energy at time 2. And it doesn't change with time. So if you have a system like this ball on this roller, under ideal circumstances, it will convert potential energy from height to kinetic energy of motion and back. However, you'll see it's losing height. But you're also hearing noise because it turns out this actually has a whole bunch of friction, which is turning things into noise and heat and stuff. This isn't the best demonstration. A little better would be I could set up a pendulum. Now this swings back and forth generally to the same height each time. Not quite. But there's air resistance and stuff, and energy is lost to heat. But in ideal circumstances, you'll just have potential and kinetic energy, and you'll be able to work out things based on conservation of energy. So we'll deal with ideal systems where energy is only in kinetic and potential. This basically never happens in real life. You can make it happen on very small scales, things like that, but in general, there is some form of friction and energy gets lost to heat. But this is a good approximation. And if friction is low, this is a good approximation. And this gives you an idea about how energy changes from one form to another. So equation-wise, when energy is conserved, we have kinetic 1 plus potential 1 equals kinetic 2 plus potential 2. Because, energy total 1 equals energy total 2. So this is 1/2 mv1 squared plus mgh1 equals 1/2 mv2 squared plus mgh2. And this lets you solve problems without having to go into the details of like acceleration and stuff like that. You can just solve problems with energy. So for example, if you drop a stone, as a stone falls from a height of 10 meters, it will steadily speed up. And you can calculate what that speed should be as a function of the height, because the total energy, kinetic plus potential, will be the same at all heights. So you can calculate the kinetic energy and you can calculate what the potential energy is and thus figure out what the kinetic energy should be. So at the moment the stone is released, the total energy is equal to the potential energy, because at the moment a dropped object is released, like right now, this pen has no kinetic energy. And as it falls, it converts potential energy into kinetic energy. And then it hits the ground and bounces and stuff. So at the moment the stone hits the ground, all the energy is kinetic and nothing is potential because it's at a height of 0. So we can work out potential and kinetic energy at every height. So at 10 meters, the potential energy is 9.8 joules. The kinetic energy is 0. At 7 meters, the potential energy, 0.1 kilograms times 9.8 meters per second squared times 7 meters is 6.9 joules, which means the kinetic energy is 2.9 joules. At 3 meters, the potential energy is only 2.9 joules, so the kinetic energy will be 6.9 joules. And at 0 meters, the potential energy is 0 joules, so the kinetic energy will be 9.8 joules. So because total energy equals kinetic energy plus potential energy, kinetic energy will equal total energy minus potential energy. So our experiment next week will be related to this. We'll drop a rock, or we'll drop a ball in the stairwell, and we'll calculate potential and kinetic energy. You'll see how one goes down and one goes up. And they're not going to perfectly match because reality, there's energy loss to air resistance and stuff, and issues with our accuracy of measurement. But here, at a height of 10 meters, total energy is 9.8 joules, potential energy is 9.8 joules, kinetic energy is 0. As it falls down, potential energy decreases, kinetic energy increases, and the total stays the same. For an ideal pendulum, at one end of the pendulum, at the high end, maximum potential energy. At the bottom, maximum kinetic energy. Back up on the other side, again, maximum potential energy. And back and forth. So potential energy, mgh, gets converted into kinetic energy, 1/2 mv squared. And we can use that change in potential energy to calculate the speed or the magnitude of the velocity. And because potential energy doesn't care about path, all we care about is the change in height. This lets us solve problems where we have some weird movement or some unclear path. So when you have something that drops 1/2 mv squared equals mg delta h. So the final velocity for a dropped object is 2g times delta h, or something that started at rest. So this formula works for, if I drop something from a height, but it also works if I rolled it down a frictionless slide or something like that as well. Because again, path doesn't matter, just the change in height. So here, if you have a 25 kilogram child that goes down a 3 meter tall slide, what's the kinetic energy of the child at the bottom of the slide? And what's the speed of the child at the bottom of the slide? You could assume that at the top of the slide, at 3 meters high, the initial kinetic energy of the child is 0. And at the bottom of the slide, at 0 meters high, the final potential energy of the child is also 0. So we know that kinetic energy 1 times potential energy 1 equals kinetic energy 2 times potential energy 2. We also know that kinetic energy 1 is 0 because we started at rest. Child starts at rest at the top of the slide. We know that potential energy 2 is also 0 because at the bottom of the slide you're at height 0, so the potential energy is 0. Why are you not? So those two cancel. So potential energy 1 is mgh. That's our initial potential energy. That will also equal our final kinetic energy. So our final kinetic energy will be our initial potential energy, which is 25 kilograms times 9.8 meters per second squared times the height, 3 meters, which is 735 joules. So we know our kinetic energy at the end is 735 joules. We can now use that to figure out the speed. Kinetic energy is 1/2 mv squared. So velocity squared is 2 times kinetic energy over mass. So the velocity is going to be 2 times the kinetic energy over the mass, the whole thing in the square root. So we take the kinetic energy, 735 joules, 2 times 735 joules divided by 25 kilograms gives us, when we take the square root of that, about 7.67 meters per second. So you slide down a 3-meter high frictionless slide, you'll be going at a nice quick riff of 7.37 meters per second. The other way you can do velocity is 2g delta h, which gives you the same. You have a 1 kilogram ball traveling at 3 meters per second. So here we're starting with kinetic energy. It rolls up a ramp. How high will the ball travel up the ramp when it comes to a stop? So we have a ball rolling up a ramp, a 1 kilogram ball traveling at 3 meters per second, and it rolls up a ramp. So how high will it roll up the ramp when it comes to a stop? So here we're going from kinetic energy, 1 kilogram ball moving at 3 meters per second, to potential energy. So here, our initial potential energy is 0. Our final kinetic energy is 0 because it starts at the bottom of the ramp. So initial potential energy is 0. Final kinetic energy is 0 because it's come to a stop. So we get 1/2 mv squared. That's our initial kinetic energy equals mgh, our final potential energy. And we want to find height. A little bit of algebra tells us that height ends up being v squared over times g. So 3 meters per second quantity squared divided by 2 times 9.8 meters per second squared gives us 0.459 meters. The initial kinetic energy is 4.5 joules. It turns to 4.5 joules of potential energy. 4.5 joules of potential energy for 1 kilogram ball is a height of 0.459 meters. And the nice thing about these, in general, mass cancels. So often you don't have to worry about mass at all. Here we have a 1,000 kilogram car traveling at 2 meters per second, and it rolls down a 4-meter high hill. What's the speed of the car at the bottom of the hill? So here we have a situation where we start with both kinetic energy and potential energy, go down this hill, and have only kinetic energy. Again, initially we have both potential energy and kinetic energy, and we convert all of it to kinetic energy. So in this situation, we have mgh plus 1/2 mv initial squared equals 1/2 mv final squared. You can divide through by mass, so you don't have to deal with the 1,000. And I also multiplied through by 2, so 2gh plus v initial squared equals v final squared. And so v final is going to be the square root of 2 times gh plus v initial squared, or 2 times 9.8 times 4 meters plus 2 meters per second squared. So 78.4 meters squared per second squared plus 4 meters squared per second squared, which is 82.4 meters squared per second squared, which comes out of a final velocity of around 9.08 meters per second. Now here is a question you can ask. You're designing a roller coaster. How fast does a 300 kilogram roller coaster car need to travel to be able to roll over a 20-meter high hill? So you want your roller coaster car at the bottom of the hill to have enough energy to get over the hill. So how fast does it need to be traveling at minimum? Now, obviously, in practice, you'd like it to be going faster than that number because you wanted to make sure it gets over the hill without any trouble. And it doesn't, get slowed down by friction or something. But in this case, you start with only kinetic energy, you end with only potential energy. But the given information is about the end. You're working backwards. So here, again, 1/2 mv squared equals mgh. But what we know is the final height. We're trying to find the initial velocity. So velocity squared equals 2gh. Velocity ends up equaling the square root of 2gh. So the square root of 2 times 9.8 meters per second squared times 20 meters. Because again, mass cancels. Velocity is square root of 392 meters squared per second squared, or 19.8 meters per second. Lastly, we're going to talk about a pendulum. If you have a pendulum that started swinging at a height of 10 centimeters above the bottom point of the swing, we want to find the speed of the pendulum at the bottom of the swing and how high the pendulum goes up on the other side of the swing. Remember, 10 centimeters is 0.1 meters. This is much like all these other problems. Figure out the speed of the bottom of the swing. Potential energy initial equals kinetic energy final. So mgh equals 1/2 mv squared. V squared equals 2gh. V equals square root of 2gh. The square root of 2 times 9.8 times 0.1 meters comes out to 1.4 meters per second. Now for the height at the other side of the swing, well, potential energy initial equals kinetic energy in the middle, which equals potential energy at the other end of the swing. So mgh1 equals mgh3, h1 equals h3, which is 10 centimeters. the height will be the same. Pendulum swings back up to the same height it reached on the far side. That was all for today. Is there anything I want to cover? No, I don't want to go into power today. So that is all for today. So I will stop sharing.